Okay, so welcome everyone to my presentation today about the validation of reanalysis data and bias correction for wind power simulation and application for the analysis of the Texas extreme freeze event last year. So first of all, I'd like to briefly introduce myself. I'm a postdoc at the University of Natural Resources and Life Sciences in Vienna, or in short, BOKU. I'm interested in future global energy systems and impacts of extremes and also climate change on power systems. Initially, my research was focused mostly on Brazil, but I extended this to a more global vision, focusing on validation of reanalysis data for simulation of renewable power generation. The past years, I've been working on the project Refuel. This is a project which aims at analyzing the possibilities of renewable fuel generation, where H2 from renewable power is combined with CO2 from ethanol production to produce renewable fuels. This project, apart from a techno-economic analysis, also focuses on topics relevant for society. For example, is it okay to build renewable power generation infrastructure in other countries, for example, in South America, to be used in Europe? So today you're going to hear about first of all, why do we need to validate reanalysis data, what error we can expect and how it can be reduced. And then the second part, I'm going to talk about the application of climate data for an analysis of the Texas 2021 extreme freeze event, looking at questions like, could such an event have been expected and why was the Texan power infrastructure not winterized? So as David already mentioned before, there's a strong link between weather and also weather extreme events and the power system. On the one hand, via resource availability, on the other hand, via demand, but of course also, especially extreme events have an impact on power system components. For example, they can freeze and during cold temperatures, there can be damage to infrastructure by wind or also by floods. And in order to take account of all of those factors in a long-term perspective, we need high-resolution long-term climate data. Such climate data in many cases come from reanalysis data. And of course, such data needs to be validated before usage. Just to give you an idea for which applications we have used reanalysis data in our research group, I have some examples here. For example, there's been an assessment of high shares of renewables in power systems, in particular an assessment of opportunity costs of not building wind power for decarbonization in the German-Austrian market zone. There's also been an assessment of the system efficiency of US wind turbines, or one of the core articles of our Refuel project has been the land neutral increase of renewable fuel output from sugarcane ethanol in Brazil. But there's also been an assessment of small-scale hybrid renewable energy systems in Chile. So there are various applications of renewable reanalysis-derived renewable power generation time series. And in all of those cases, of course, we need to know what error can we expect from the climate data. And this leads to the first part of my presentation today, the validation and bias correction of simulated wind power generation. So in my analysis, I used different reanalysis datasets, MERA2 and ERA5, and also further datasets for the purpose of bias correction. On the one hand, wind speed measurements, on the other hand, the global wind atlas. So just to give you an idea here about the different spatial resolution of those datasets, on the left and in the mid, you see the two reanalysis MERA2 and ERA5. And you can see here they have a rather coarse resolution. You can clearly see single pixels here. But if you compare it to the Global Wind Atlas, you can see it has a much finer resolution. You can really see lots of spatial detail. And this detail is introduced into the reanalysis data via bias correction. So what does the comparison of ERA5 and MERA2 reanalysis tell us? If you compare it to observed wind power generation in different parts of the world, so I looked at 4 different regions, focusing on regions outside of Europe, because there have been quite some assessment for Europe already, but less for other regions of the world. So here we can see that overall, ERA5 seems to perform better than MERA2. In this case, you can see the correlations, which are usually higher than for ERA5 than for MERA2. For Brazil and for South Africa, this increased correlation, there's a significant difference in the correlation. For the US, it's still a bit higher on average, but the difference is not significant. And for New Zealand, they're on a similar level. But overall, we can say ERA5 performs better, or at least as well as MERA2, and therefore should be preferred. So of course, there is always some error if you apply reanalysis data for the simulation of renewable power generation time series. And in order to reduce this error, we can apply bias correction, which I did among others with the Global Wind Atlas, 2 different versions, Global Wind Atlas 2 and Global Wind Atlas 3. And also for both of the reanalysis ERA5 and MERA2. What you see here are the bias correction factors for the US. And there are quite some things to notice. On the one hand, we can see that the bias correction factors with ERA5 are a bit higher than from MERA2. So they're a bit more in the yellow range. And also something important to notice is that in the west of the US, the bias correction factors are also higher than in the rest of the country. So there are quite some locations where the bias correction factors is at 2. So this means the wind speeds in the Global Wind Atlas is twice as high than in the reanalysis dataset. So especially in those regions, it seems to be really necessary to apply bias correction. So what's the effect of this bias correction? First of all, here we can see that with the Global Wind Atlas 2, there are different effects depending on the world region where it's applied. In 3 cases, the mean bias error is increased applying the Global Wind Atlas 2, as in the US, in New Zealand, and in South Africa. In 2 of those cases, it's shifted closer to 0, so in New Zealand and South Africa. In the US, the MBE is increased, so the error is increased. Whereas in Brazil, it's reduced, but into a negative range before the bias correction, it's around 0, where we want it to be. So the effect of the Global Wind Atlas seems to be quite different in different world regions. On the other hand, the Global Wind Atlas 3, in all cases, increases the mean bias error, always into a positive range. So an increased error seems like something bad, but what must be mentioned in this case is that for those simulations, it didn't take account of any downtimes or curtailment or anything that might reduce the power output. Therefore, we would expect some error here, actually. It seems that the simulations using bias correction with the Global Wind Atlas 3 are most reliable in this case. I also compared bias correction using the Global Wind Atlas to bias correction using local wind speed measurements in Brazil. Overall, we can say here that both of those data sets allow a reduction of the error. However, with local wind speed measurements, there are some cases where the error is increased quite drastically in Pernambuco and also for 2 of the wind parks in Brazil. So the Global Wind Atlas is more recommendable in this case, as it leads to more stable results. Something else I looked into was how the correlation and the root mean square error behaves if the time series are temporally aggregated. So of course, as we would expect, if we aggregate the time series from hourly to daily and monthly resolution, correlation increases and the root mean square error decreases. But such analysis allow us to, if, for example, only daily or monthly time series are available for validation, to derive the range in which the hourly correlation or error would be expected. So to sum up this first part, we could see that ERA5 in general should be preferred over MERA2. The bias correction with the Global Wind Atlas 2 can reduce the error, whereas the bias correction with Global Wind Atlas 3 increases the error. However, in this case might be something good because you would expect a positive error. We also saw that the global wind atlas performs similar to wind speed measurements and bias correction, but leads to more stable results. And also something important to consider is that there are quite some differences between different world regions. On the one hand, between how MERA 2 and ERA 5 results relate to each other, and also for the effect of the global wind atlas. So in an ideal case, any time before you apply reanalysis data, they should be validated beforehand to know about the error. So towards the end of my PhD, I had the chance to apply finally those simulated time series I've been working with for years. What I looked into were, on the one hand, the frequency of such events, and on the other hand, the profitability of winterization. So if we look at what happened during February 2021, we can see there was a capacity deficit for several days caused by low temperatures. So when the temperatures started to drop, the outages started to increase quite drastically. We can see here that especially wind and gas capacities were affected by outages. Initially, wind was blamed a lot, or the large capacities of wind power generation installed in Texas were blamed a lot for this event happening. But when we looked into the data, we found out that actually during the time of that event, not a lot of wind power was available anyway due to low wind speeds. So the highest fault for this event happening is due to gas capacities failing. So we wanted to look into this event in a long-term context. And for this, we applied climate data, so temperatures and also wind speeds, to simulate demand and outage from temperatures and wind power from the wind speeds. If this information is combined, we obtain a deficit model, so a model which tells us that the periods during which there is less capacity available than there is demand. And if we combine this again with the scarcity pricing model, we can derive the marginal revenues from winterization, and thus whether it would be profitable to invest into winterization. So if we put this event of last year into a long-term context, looking at temperatures and at capacity deficits, we can see that, well, of course, this event was quite extreme, but not completely unexpected. So looking at temperatures and at the minimum temperatures during the event last year, it was 12 degrees. You can see it at the bottom right. But there were other years where the minimum temperature was colder in 1951 and also in 1989. Also, the duration of the cold period, which lasted for 132 hours, was shorter than in another year, than 1983. So temperature-wise, this event, of course, it was extreme, but not the most extreme one. And then if you look at the capacity deficits, also the duration of the capacity deficit period, which lasted 106 hours according to our model, it was not the longest capacity deficit period. Again, in 1983, there was a longer period of 120 hours. Only the maximum capacity deficit of 31.3 gigawatts was the highest among those other 8 events estimated during the past 7 decades. But in other years, it was quite close, only 2 gigawatts below. So overall, we can say, of course, this event was extreme, but it wasn't totally unexpected. So using this information and the scarcity pricing that is in place by ERCOT, we can derive marginal revenues. Here you see, as an example, the marginal revenues from gas power plant and gas field winterization. So what you see here is, on the one hand, the expected marginal revenue from gas power plant winterization, which is the black or blue line. And then as a red line, you see the cost of winterization. So up to about 15 gigawatts of winterized capacity, the expected revenue is higher than the cost of winterization on average. So there can be profits. But what must be mentioned here is that the variance of expected marginal revenues is quite high. So even for the first gigawatt winterized, there is a 16% chance that there are no profits or even negative profits. And the more capacity is winterized, the higher the chance comes that there are negative profits. So there's quite some risk involved with such an investment, which might explain the lack of winterization. On the other hand, there is no penalty if the demand is not satisfied. So this is quite a low risk. If there's no investment, the only risk they have is that they might lose some revenues, but it can't be sure whether those revenues can be made. So this risk of investment could be one explanation why there has not been any winterization or not enough winterization so far. Another reason for lack of winterization might be the underestimation of effects of cold temperatures. So there have been other years where the winters were quite cold in Texas, and in 2011 and 2014, Texas also experienced some issues in the power system due to cold temperatures. Not as catastrophic as last year, but still there was quite some impact. So on the one hand, the effect of cold temperatures was known to some extent. On the other hand, there were also some unexpected effects. So for example, during our analysis, we could see that, for example, for wind turbines, and in some cases where the outages started for wind capacity, there were temperatures well above zero at the locations of wind power plants. So they actually should not have failed. And also similar for other generation capacity, the plants started to fail in regions where there was actually the rated capacity, so it should not have failed. A further reason for lack of winterization might be higher discount rates than we assumed in our model. In this case, we assumed a discount rate of 5%. We also did a sensitivity analysis increasing the discount rate to 10%. This had the effect that the capacity up to which it would be profitable to invest into winterization for gas power plant and gas fields was reduced to about 7 to 8 gigawatts. So about the half of what it is at 5%. But in reality, discount rates could be even higher. We don't know the exact value. And the higher the discount rates, the less profitable winterization becomes, and the higher the risk, of course, that negative profits are made. And finally, a further reason for lack of winterization could be strategic behavior. So if there are large operators on the power market, the more they invest into winterization, the less profits they can make additionally, because the more capacity is winterized, the smaller or the shorter the periods of capacity scarcity become. So the periods during which high prices are in place due to the scarcity pricing, and therefore no additional profits can be made. But in reality, there are no such large operators in the Texan power market. Therefore, this reason is implausible. So to sum up, we could see that this extreme event last year in Texas was extreme, but not completely unexpected. We identified 8 other similar events within the past 70 years of climate data. We also showed that on average, winterization is profitable, and especially winterization of gas power capacity is important, but there hasn't been investment due to different factors. So this shows us that the market mechanism failed in this case, and therefore legislation is necessary to secure the supply in the Texan power system. If you want to know more about this, you can refer to our publications or just ask me afterwards in the discussion. Thank you.